How multi-head attention scales the algorithm. Multi-head attention is a key component of the transformer architecture, which has become foundational in modern natural language processing, NLP, and other domains. The concept of multi-head attention improves upon the basic self-attention mechanism by enabling the model to focus on different parts of the input simultaneously through multiple attention heads. This not only enhances the expressiveness of the model, but also helps scale the algorithm effectively in several ways. ###1. Parallelization across attention heads. In multi-head attention, the input embeddings are linearly projected into multiple query, key, and value spaces, and each head computes attention independently. These computations can be parallelized across different attention heads. Since each attention head operates on its own set of projected vectors, the computation for different heads can happen concurrently. This allows the model to take advantage of modern hardware accelerators like GPUs or TPUs, which excel at parallel operations. By splitting the attention computation into multiple heads, the workload is distributed, making the overall computation faster and more scalable. ###2. Increased representational capacity. Multi-head attention allows the model to capture different types of relationships between tokens in the input sequence. Each attention head can focus on a different kind of pattern or relationship, e.g., syntactic versus semantic relationships in NLP tasks. By learning diverse representations across heads, the model gains richer and more expressive representations of the input data. This increases the capacity of the model to handle complex tasks without requiring an exponential increase in parameters. As a result, multi-head attention scales the representational power of the model without needing to rely solely on deeper architectures or larger hidden layers, which could otherwise lead to diminishing returns or higher computational costs. ###3. Dimensionality reduction in each head. In multi-head attention, the dimensionality of each attention head is typically smaller than the full embedding dimension. For example, if the embedding size is d_model, it is common to split it into h heads, where each head operates on a reduced dimensionality of d_model/h. Reducing the dimensionality per head makes the computation of attention within each head more efficient. Although there are multiple heads, the total computational cost remains manageable because the attention mechanism is applied to lower dimensional spaces. This approach balances computational efficiency with the ability to capture diverse patterns in the data. ###4. Scalability with sequence length. The standard self-attention mechanism has a computational complexity of $O and squared, $ with respect to the sequence length $, since it involves computing pairwise interactions between all tokens in the sequence. While multi-head attention does not directly reduce this quadratic complexity, it allows the model to better exploit the available information in long sequences by focusing on different subsets of tokens in different heads. This can improve performance on longer sequences without increasing the computational burden beyond the inherent cost of self-attention. Additionally, recent advancements, e.g., sparse attention, linformer, longformer, etc., have built upon multi-head attention to further address scalability issues with long sequences by introducing sparsity or approximations to reduce the $O and squared $ complexity. ###5. Improved gradient flow and training stability. Multi-head attention introduces multiple pathways for gradient flow during training. Since each attention head operates independently and then concatenates their outputs, the gradients from different heads can provide complementary signals that help stabilize training. This improved gradient flow contributes to better convergence and more stable training dynamics, especially as models grow larger and deeper. This stability is crucial when scaling up the model size or dataset size, as larger models are more prone to optimization challenges. ###6. Flexibility in model design. Multi-head attention provides flexibility in designing models for different tasks. For example, in encoder-decoder architectures, like those used in machine translation, separate attention heads can focus on different aspects of the source and target sequences. This flexibility allows researchers to experiment with different configurations, e.g., varying the number of heads, head dimensions, etc., to optimize performance for specific tasks while still maintaining scalability. Summary. In summary, multi-head attention scales the transformer algorithm in several ways. It enables parallelization across attention heads, improving computational efficiency. It increases the representational capacity of the model by capturing diverse patterns in the data. It reduces the dimensionality per head, balancing expressiveness and efficiency. It provides better gradient flow and training stability, which is important for scaling to larger models. It offers flexibility in model design, allowing for task-specific optimizations. These properties make multi-head attention a powerful tool for building scalable and efficient deep learning models, particularly in domains like NLP, where handling long-range dependencies and complex relationships is critical.